Hey there, and welcome back. I just noticed a couple of mistakes while rewatching this, but I put them in the description here of that video. You can't use things like brackets and arrows and stuff, but I found these symbols that kind of look right. Put in the description. There's an annotation dealing with that. So I'm just going to go on now with those functions. I'm letting this load up. So I don't know why, but I like to make sure that everything gets loaded fine and watch it through. Yeah, I can use one of my favorite features. This is a little utility I wrote to put things in this little area here. What do we call this? Not the task list, but anyway. System tray. It's called the system tray. You know what's great about the system tray is that things that are in the system tray are not in this list, you see. And, as well, you see these things. Let me bring that back. When this is here, I can't make another, I can't make another one of these guys. No, I don't really need to because this is a tabbed document kind of thing. But for my command box, sometimes I want a second one, so I can take it and put it in the system tray here, and then this becomes enabled again. So now I can have two. See? Anyway, I don't really need two though. At the moment, and I don't want to see that. I don't want it in the list. And I don't want to see this. Well, another thing I noticed today was this view, and it's not really that. It used to be much prettier, actually. The group by category view. But these things are called file folder, and I always want the folders on top. So I thought, well, because it's called file folder, it doesn't appear first in the list because it doesn't start with, as I changed it to the letter A. And if that bothers you, and if you want to change that on your own, it's really very easy to fix it. You have to go in the registry though, unfortunately. And search for file folder. And I'll show you where I made the change. It's a reversible. It's a reversible change. And all it is just changing where it gets the name from. Well, let's do that. I can go back to here. Okay, so I addressed those errors. Also, I should mention that I did mention that if I'm passing regular old multi-byte strings into puts, then certainly if I'm passing T strings into something that prints, I should use the tcar version of puts, which happens to be this. For some reason, this one doesn't start with a T. It's put T string. I think that's the way you look at it. But it's not one. It's not. That function isn't one that starts with the word stir, so it kind of makes sense that the TS is at the end, but the underscore remains where it is. Alright, so more of those functions. Now we got all these. Oh, here it is. It's this friendly type name. All I did was put an underscore in front of this and made a new one and just said a file folder, and that was it. Now the folders appear in the top of the list. Okay. Now, done equals. These arrow things are for later. The simple ones. We know this. This is the functional version of the cast. Sometimes it's a pain to type this out, and easier, in fact, when necessary, to call a function. Now, len is this. Although it returns the member mlen, even if it wasn't returning the member, it would be the equivalent of strlen tcar version. So tc strlen. See? That's what it would be, but it's slightly optimized. Oops, you know what the length is already. And this is of type SizeT. Now, if you've ever used something called MFC, Microsoft Foundation classes, those classes gave the length in integer format. And in fact, you'll find that oftentimes, you'll want it in integer format. And I'm starting to make it a habit to make int versions of functions rather than this SizeT. This SizeT is a bit of a pain, and ints are much easier to deal with. Yeah, they can be negative. So what? They can be negative. Now, all of these are very similar to the ones that you would find in MFC. In fact, I think, aside from these two, that their find function starts with a capital S, and they all return ints, capitalized. I don't know why they do that, but they do. And you'll notice, by the way, that I have a different color for some of these types, not for any type. And there's a place where you can set what they call the user-defined types so that they appear in a different color. And it's not just to make things pretty, it helps you catch spelling mistakes as well. And where that's located is wherever you installed the compiler. Do I have something to take me there? Bin. Anyway, I know sort of where it is. Here, I guess. Just want to make sure I get to the right one. I think it's this one. IDE. Yeah, that's the file. User type.dat. This is just a text file, and anything you put in this text file, it's going to come up in that funny color. And I got a bunch of things in here that I've added over time. Some of them I probably don't want anymore. This I don't want. Certain things, yeah, well, I'd like to get rid of that. If you're making all these various types, you're going to find that it really helps when the color changes, and then you know you didn't spell something wrong. Okay, so just adding things in there will change the color. I'll bet you have to stop and restart the program. Okay. Now, which next? So GetLength is null. Now this brings up an interesting little question, conundrum. Because it is possible that this MP string doesn't have to be null. Now I know I said that we don't want to do allocations in the default constructor, but there's a type of way of doing this sort of thing, so that this doesn't have to be null ever. And basically, the idea is that you allocate a little bit of space in your class. In fact, this technique is an optimization technique. It's given a special name, SSO, called the small size optimization. Okay, now why don't I just go ahead and do it? Well, there's a reason, and I don't know if it's a good reason. I think I might do it. But one of the things that this class doesn't do is you can't pass it as a real string to something like printf. If you tried printf, hello %s, and then put one of our strings in here, it's not going to work. You'd have to call the cast to turn it into a string. But there's a trick that you can use to make this actually work. But if you use that trick, you have to throw out the small size optimization. But you gain another kind of optimization in the process. And the trick is basically that you don't allocate a string as I have here. But you allocate a string basically, right? But the thing that is the string where the text goes is some distance along. So let's say that you allocate a string of the length that you want. So first there'll be some header part with some information about the string, and then the data part. Oops. Like this. Okay. And the pointer that's stored in the class points here. So here's your pointer in the class. Now the class knows about this, so it knows that in order to find the allocated, the head of the allocation, it's back here somewhere. Okay. So that's no problem. And in that case, for instance, the length could go in this header. So you can move that into here, and you might have other information, important information, like how much data you've allocated. For instance, when you're resizing the string, if you add one extra byte, is it really worth it to do another allocation? And generally it's not. Generally you allocate a little bit more, and there are different algorithms for knowing when is a good time to add another chunk, and the bigger the thing gets, the bigger the chunks get, and so on. And a different way for when you're removing things. And when you do the allocation this way, since there's only one member and it's pointing to a string, then you can call it with printf, and it'll work fine. So in every respect, it acts like a string. The other thing, for instance, in MFC, what they do in this header part is keep a reference count. So when you pass the string to a function, instead of copying all the data, all it does is increase that counter in here, so that if that function doesn't modify the string in any way, copying needs to be done. If any modifications occur, then it has to make a copy. But most of the time you're not copying, so that's another benefit of this. But doing it this way, I think would have to require that whenever you make one of these strings, you'd have to allocate some data. And the question is, what's the trade-off? If you're working for it, suppose you're designing software for a company, and the company software is like running in a store system, like a supermarket checkout or something. And so therefore this software is running for months or years at a time. Alright. The small size optimization, which is, let's say, allocating 30 bytes, that's a tiny amount of bytes. So you just have tcar small buff. Okay, and you can figure out over time what's a good average size for your strings. And if your strings are generally around this size, then you just use the buffer, and you don't use the local buffer, and don't do any malloking. And so what that means is that literally millions and millions, maybe billions of allocations are cut out by this tiny little extra buffer that's taking over most of the strings. And for a computer system that's running, or a program that's running for months or years at a time, that savings in allocations reduces the what they call the heap fragmentation, which is what causes systems to eventually bog down and grind to a halt and have to be restarted, pretty much goes to zero. Because almost all actions in a system like a store system or something are string things. You're printing something out on a roller tape, or adding up the bill or whatever, and you're just making these little strings and copying them back and forth. If all that's happening on the stack, you get no fragmentation, and it's a much more the trade-off is in what you lost in being able to do printf, which is hardly anything. I can add this CSZ here, big deal. But what you're gaining is a system that's stable over years. But if all you're making are little utility functions, little utility programs that only run for, their lifetime is a few minutes, and then people go on and do something else, then it'd be more, you'd probably want this kind of a scenario where you don't have to think anymore about casting or anything. It's just a string. And you get this extra piece of header data. So it's a conundrum, and I'm not really sure what to do as far as what brought me onto this topic, whether or not we should allow there to be null strings. I'd prefer no null strings. I would go with a small size optimization, I think. I can show you in one of my other projects a place where I use that particular small size optimization. It's on a buffer, not a string, but same idea. This will load up. Oh, here were the corrections, by the way. These were the corrections from the... Oh, here we go. Buffer. Yeah, okay, so here, 16 bytes. This code actually comes from a time when I was working for a particular company, and we were having problems with systems slowing down over time and eventually having to be restarted. And I added this little 16-byte buffer to the little buffers that were used quite a lot. And that was the end of it. They never had to restart the system ever again. Never once. It fixed the problem. Because the thing was doing an allocation every time it was invoked. And there would be these loops that are constantly running in the process. And, somebody just happened to have one of these, or would tend to have either one of these declared or as part of something else sitting on the stack, not necessarily to be used, just a local variable. And so when you're going around through a loop, any kind of loop is a enter scope and a leave scope type of scenario. So there are constant allocations. Maybe the zero allocations didn't matter so much, but still, these buffers were part of many different structs, and usually they only contained a few bytes of data. And so that putting it on the stack, putting a little bit on the stack, just solved the problem. And you see this here returns a pointer to the buffer. And I know that if the size is less than that particular limit, to return the thing from the stack. Otherwise, if it gets bigger than that, then I have to use malloc. That's this resize somewhere that calls malloc or realloc or something. Anyway, a lot of issues come up with these memory manager things. is empty, that's obvious enough, blank here. What I mean by something that's blank is a string that doesn't really contain anything but white space and carriage returns, tabs, spaces, things like that, whatever I define. Could use a blank space, maybe. This might be a better definition for that. No, don't know how this contains only works, but the wording should be clear enough. Does the string contain only things within this set? Then it returns true if that happens to be the case. Now I'm trying to go from, I'm not showing you these functions. Well, actually I am showing you. These are all in line, so you've seen these, except isEmpty, where is that? Isnull or length of 0. Okay, so that leaves, as far as this list, how does this work? Contains only. Now, this first part is just asserting that the string passed in is not null or not empty. Ref assert is a macro I made that it causes an assert to go on if the expression is false, but rather than crash the program, it returns. And in release mode, it also returns. So this is not debug only. This is asserts in debug and returns, and also in release mode it returns. So this is a little bit of a badly named macro. Now, if not is empty, that shouldn't really have to be saying that. In fact, I don't have to say that, do I? It can't be empty if it's, I just check to see that it's not null and there's something in there. Now, StairsBack. See how easy it is to figure it out? StairsBack, taking this object as a string, and if you don't remember what that function does, press the help, which never brings up the right thing, but you never know. Ah, it works. StairsBack returns an integer value specifying the length of the substring in stir, consisting entirely of characters in CRT. CRT, the second thing passed in. Now remember, this said contains only white space. So here's our string. This is the white space. And this is going to return the length of the string consisting only of white space. And if that length is equal to the length of the entire string, then the string contains only white space, or any set of characters you put in there. Now it's not the same as this function. This is something that says the string contains only these types of characters, and this is a test to see if the string contains at least one of this set of characters. Now, does that work? Same assertion at first. I don't know why I've got this here, because I'm already checking that. Find the first one of these things, and here I'm using MFC style. an MFC style function. They're always capitals, and they return ints, and -1 means not found. So let's step into here. First, I'm retrieving the string value for our thing, and then taking this. Okay, so this didn't have to be written this way. The reason there's no reason to save this up. To make it more readable, I could put it this way. That I guess I didn't want to call the function twice. I don't know, but that's what that says. Okay. So now, what does this do? This is strPBurk. I don't know where they came up with this name, but this scans strings for characters in the specified set. Okay, so this thing quits its search as soon as it finds anything in this set. Returns a pointer to the first occurrence of any character in the set, otherwise no. If there are no common characters. So essentially, yes, this is looking for common characters between these two sets. When it returns no, that means there were none of these in this. So no, return -1, otherwise return the difference between the found position and the start position, and that would give you the position of the first of one of these. It doesn't tell you what it is, but one of them. Now we'll get back. Okay, now this doesn't even care about what the return value is. All this says is if it's not -1, found 1, so therefore there is something of this type in the string. For instance, you might say if stir contains any operators, like brackets and plus and minus, then do something or other. Maybe it's a mathematical expression, or maybe you're something like that. An example. FindFirstNot. I don't know if you can hear me, this rain, but it seems my microphone cancels out the noise pretty good, so probably you don't hear it. FindFirstNotOf. Find the first thing in the string which is not in this set, what that says. Now that's a simple immediate function we just call StairsBack again. Whoops. Returns the index in the string of the first character in the string that does not belong to the set of characters. It's the one we just looked at. Whoops. So that index, whatever it is, gives us the position of the first character not within this set. This one, again, I had to write myself. I don't know. I think I mentioned this before. Same idea, but starting from the end. Somehow, if you can think backwards, this is what comes out. It looks messy, but I start from the end, and I go through the string, and what I'm trying to find is the last occurrence of a character which is not in that set. I always get this, have a hard time. Okay, well, starting from the end, if this thing goes all the way through and doesn't find one of these, then it will have gone all the way through the length of this, exhausted this string searching for something, and got to the end. And if that's true, then that position is not one of these. And if I started from the end and went backwards, then that must be the last position in the string that does not contain one of these characters. See, generally speaking, think of it this way. If I find one of these characters, ever, starting from the end, this will not be true. And so therefore, this is the end of the string. And suppose it's usually a white space. Suppose there's this amount of white space. Okay, and then the text ends here. The last letter of text is here. Something like that. And everything from here to here is going to be a character which is within the white space set. So I start from the end. At each of one of these points, this loop is going to break before it hits the end. So this will not be true. It'll continue on. And eventually, when I get to the letter D, which is not white space, this will go exhaustively through, hit the end, and this will become true, and that will be the last position in the string, which is not a white space character. The remainder of the string is all white space. Difficult. All those negatives. Alright. First off, that's easy. That's like this contains any. In fact, it uses the same function. FindFirstOf uses that word or name function. Take the difference. Now these indices are important for searching for things like substrings and so on. And so I needed to get a good set of at least functions which search for sets of characters. For instance, for trimming. In fact, with these three already, we have trim, which is where I could go next. and then I'll leave it at that. TrimRight, TrimLeft, and trim. So yeah, let's just see an example of one in action. Get rid of all this junk. I'll still return 0 there. So let's start with a string. So I want to add some white space at the beginning. Could have tabs, if you like. Then some text. Oops. And maybe some more white space at the end. Might be a character and line feed. And I would like to print that out. But I would like as well, these things kind of get in the way. Let's use tab. On the sides, I'd like to put some of those bars. So you can see the white space. Alright, so that's the text. I'll add another tab in a different spot. I want to make it a little bit bigger. Not so centered. Okay. Now, if I call TrimLeft on that, now that should occur before this sum happens. So I think that should be okay as it is, because it's going to evaluate this before adding. And so there, you can see the left side got trimmed, or if I do right, the right side got trimmed. So combining the both, we just have one function. Which does it all in one step. Now this is useful if you're reading in text lines from a file, line by line, and you just want to clean up the sides and only deal with the text part. As for instance, if you were trying to parse this file, get rid of all this stuff on the side and then deal with just the text. Okay, now how does that work? You only really need to understand one of these to get all of them. For the right side, I find the last character, which is not a white space, and it turns out in this case. If that last position turns out to be a 0, and I'm scanning backwards, that means I scanned through the entire string and found nothing but white space. So in fact, I have a function now for this called clean, or clear. It does that. Pre and default. Yeah. So if that's true, then clear. Nice. Actually looking quite small. Otherwise, if the last position is not equal to the length, if it's length, that means that I didn't find any white space. Then I'm using this mid, which is cuts out pieces of the string. Mid is a substring type function, which I'll get to later. Too complicated for now. To understand how it works, it takes a starting index and a number of characters to extract from the string without modifying it. So this actually is a brand new string which I'm reassigning to myself, going from 0 to the position where I found the last non-white space. Okay, I know this is difficult, but for the left it's similar. Same idea. In fact, it looks almost the same. The only thing that's changed is the name last turned to first. That's why these functions were designed in the first place. The difference again, or the difference in this case, is that instead of taking a substring from the beginning, this takes the substring from the tail. So I want to cut out the white space in this case by taking a substring which starts at position, the found position, and this is a function which has a default parameter. Oh no, I have two functions, but it's like a default parameter. In the case where it's one parameter, it just takes the remainder of the string. Alright. Now, trimming simply combines the two operations. I'm going to go through one more, I think. I guess not. I used a lot of time, and it's raining again. But you're getting an idea. And this code has been uploaded. I'll occasionally make another zip and keep adding to that same directory. So you can always get whatever the latest version of this code is. Okay. See you again.